So, hi everyone. I know you just heard my name a bunch of times, but I'll introduce myself very quickly again. My name is Katie, and as Dana has already told you, I am the outgoing co-director of Science in the News, so this organization has been a big part of my life throughout all of grad school, and honestly the most impactful part of grad school for me. I started college as an English major, but I quickly learned that science was not the dry, boring, rote memorization I was taught to think it was in high school. It wasn't just about going to the back of the textbook and memorizing the glossary, which is true story how I studied in high school. But I've since come to love science for how dynamic and fascinating it is, and I hope I can show you a little bit of that today with my lecture. I hope you'll laugh, because I have a lot of really terrible dad jokes in here. I'm lucky to be talking about fecal transplants, so there are all kinds of poop jokes. So please laugh at me all you want, even when I'm not necessarily intending to be funny. I can tell I'm not going to be able to hear you as we go along. Okay, please let me know if I'm not speaking loud enough. Yeah, that's very important. I study tuberculosis in my day-to-day lab work, but I used to work in a lab that studied the gut microbiome of mice. And so I'm really thrilled to be talking to you about this subject today. All right, and with that, I will dive in. So I know a lot of science starts with hypotheses, but today I'm going to start us off with a hypothetical. So say you have a disease and it's really, really terrible. You are in some pretty dire straits and you're having diarrhea, abdominal pain, and your doctor tells you that if you don't get this resolved, there could be up to a 20% mortality rate. And if you do decide to pursue treatment, up to 3% of people actually have to have their entire colon removed to cure this condition. And for those who don't resort to this kind of surgery, if they're taking drugs, there's a 20 to 35% recurrence rate. So even if you take that full course of drugs, 20 to 35% of you are going to get this condition again, and you'll suffer all the conditions I listed above. Doesn't sound super appealing. I don't think any of you are going to be signing up for that anytime soon. And this looks pretty bad, but what if I tell you that there's something else you could be doing to treat this condition that actually has a 90% cure rate with just a single dose? Would you do this treatment?
Yes. Yes.
Sounds pretty good, right? And based on the title of my talk and the really punny abstract I put on our website, you can probably already guess that this treatment is, in fact, a fecal transplant, or in this case, a poop pill. So if I'm telling you now that this 90% cure rate treatment is basically putting someone else's feces in your body, how many of you are still signing up to do this at this point? Great. All right, the stock is going to be fun then. So, but of course, the important part of what's on the inside of this pill isn't just the fecal matter that we dump into our toilet on a daily basis. It's about what's on the inside of this lovely package. And by that, I mean the gut microbiota. And so the gut microbiota is the community of microorganisms that lives in the digestive tract. When we talk about the microbiota, we're talking about this entire community of organisms that shares our body's space. And I'll get a little bit into that later, but I just want to tell you now that we'll be focusing on the microorganisms that live in our gut. And they're really all over our body, but we're going to just zero in on that one location because there's already plenty to talk about just in that one spot. And the beautiful thing about the gut microbiota, the reason this term may sound familiar to you already, is because the gut microbiota and changes in the gut microbiota have been linked to pretty much countless health conditions, both good and bad. And this is just a very small sampling of the various conditions and syndromes in which the gut microbiota has been shown to be altered from a normal state. And that makes it a pretty important cornerstone of health. And really, in just the past couple of decades, have we really begun to unravel the importance of the gut microbiota and how it is actually affecting all these different conditions and more? But what I'd like to do in my talk today is give you an introduction into this science and how we can actually apply it to improve our health. So in my talk today, I'll start off by giving you all a brief introduction to the gut microbiota. Second, we'll be talking about how we actually acquire these microbes from the day that we're born. Third, we'll talk about fecal transplants, and just the word poop will be thrown all over the place, but luckily no actual feces will be thrown. And finally, we'll just give a really quick overview of two of the really exciting directions that fecal transplants and general research on the gut microbiota are going nowadays. All right, so just to start us off, an intro to the gut microbiota. And the way I really like to think about the gut microbiota is friends that are pretty much with us from birth. You're not as alone as you think. There are actually trillions of friends that you have with you for every nap that you've ever taken, and know every song you've ever sung in the shower, and are in every selfie you've ever taken. You just may not have noticed them. And that sounds maybe a little creepy, that the call is coming from inside the house, but I'm here to tell you that all of these invisible friends are actually here for your overall benefit. And the amazing thing about the microbiota, all these other organisms that share our body's space, is that they're as much a part of our body as what we think we really are. And let me explain that very confusingly worded sentence. So in the human body, we know there are roughly, and this varies a little bit from person to person, but there are about 37 trillion human cells. These include the skin cells that you can see brushing off your arm, the cells that make up your hair, the cells that make up the inside of your mouth. But there are also 37 to 100 trillion microbial cells. These are the bacteria and viruses that also share your body's space. And just for some perspective, these 37 to 100 trillion microbial cells can compose up to 2 to 5 pounds of your body weight. And I realize that may not seem like much if they're 50% of the cells in your body space, but if you think about the fact that these cells can be like 20 times smaller than your cells, that's actually quite staggering. And so that 2 to 5 pounds, it's a lot. And for more perspective, your brain, arguably the most important organ in your body, weighs about 3 pounds. So there may be more microbes on you than there is brain. And the really incredible thing about these microbes is while they're all over your body, they're super concentrated in one particular location, and that's in your colon or your large intestine. So if we zoom in a little further, we know that these microbes are kind of hanging out, and this is just a depiction of our gut cells, not super important in terms of the exact anatomy here, but even though we can't see them with the naked eye, they form an enormous part of our body's system. And you may think that this is a little bit of a strange concept. I think, I was raised to think if bacteria are on the inside of my body, that's a bad thing. That means I have an infection, that means I'm gonna be sick. But this actually is in keeping with the idea that microbes are supposed to be on the outside of our body. The inside of our colon is actually our outside. I like to think of the human body as a giant donut. And that hole in the donut starts at the mouth and ends, where that tube ends, the anus. And even though the donut is not exactly proportional to the human body, you can kind of think of all these microbes that inhabit this space with us as being the powdered sugar or the sprinkles on the outside of this donut, and they even coat the inside of that donut where the donut hole is being lifted out, and that's basically your entire digestive tract. So we're basically sitting in a room full of donuts. And these microbes are so populous on our bodies because they're important for so many things. They're involved in pretty much every aspect of health, as I've mentioned before, and I really don't have time to go into every single way that microbes are known to affect our body, but I do want to list some broad categories that we know the gut microbiota is important for. So I know that the things listed on here are things that are really important to existence: digestion and metabolism, immune function, brain function. All of these things you of course get credit for as humans. You're hard at work doing all these things, but really microbes are responsible for an enormous proportion of these functions. And to start us off, to set us up for the rest of the talk, I really want to go a little deeper into this idea that gut microbes play an enormous role in digestion and metabolism. And so, from kind of a bird's eye view, we know that we wouldn't get the same nutrients and vitamins and calories out of our food if we didn't have gut microbes in our digestive tract, and especially those super important gut microbes that live in our colon, where a lot of digested food matter ends up. Our gut microbes help us manufacture vitamins, including vitamin K. A fun fact is that a lot of babies will get a shot of vitamin K right after they're born because they don't yet have gut microbes that are producing it for them. They also help us absorb essential minerals. They break more energy out of food, and overall, they produce a ton of essential molecules that we can't actually make ourselves. One really critical example of this talks about why fiber is so important. So, going off this idea that gut microbes are producing things that we can't produce ourselves, the reason fiber is so important is because it's kind of the fodder for these microbes to perform these essential reactions. So when you eat something with fiber, that could be a piece of fruit or a sweet potato or a cupful of beans, the ultimate end product of fiber that's so important is this thing called short-chain fatty acids. And short-chain fatty acids are these molecules that do a ton of different things across the body. Even though they're made primarily in the gut, they have really far-reaching effects. They not only feed our gut cells, but they help kind of bolster our immune function and make sure that we're really able to fight off disease when it comes to attack. And the really important thing I want you to note here is that these short-chain fatty acids are crucial, but we can't get them out of fiber without the existence of the gut microbiota. And so to explain this process, I'm going to take a step back and talk a little bit about carbohydrate digestion. And when we talk about carbohydrates, those are basically the sugars in our food. So food can be kind of broken down into three big macromolecule categories: carbohydrates, fats, and protein. Carbohydrates are in pretty much all the food we eat, unless all you're doing is drinking straight olive oil. That's pretty much just fat. But carbohydrates can be broken down into two very big categories. And the first category is simple carbohydrates. By simple, what we really mean is just there are single or double sugar units. And the sugar units I'm talking about are going to be represented here by these purple hexagons. So simple means there's either just one sugar unit or two sugar units that are linked up. Anything more complex than that is going to be, spoiler alert, a complex carbohydrate. But our simple carbohydrates are fructose or sucrose, the things that are found in added sugars. So they're going to be in candy and baked goods as well as fruit. And these are often the carbohydrates that doctors tell us to eat in a little more moderation. So these are going to be the ones that get absorbed into the body very quickly because they're in simple enough units for the body to use them basically right away. Not a lot has to be broken down. This is kind of the base unit, and that's something our body can use immediately. So if you eat a ton of candy, that's kind of why you get a sugar rush, because these molecules enter your system so quickly because they don't need to undergo extra processing before we can use them. We can compare this to complex carbohydrates, and again, these are simply complex because they have more than two sugar rings involved, and these carbohydrates are the ones that are slower digesting. As you may have guessed, they're slower digesting because we have to kind of break them down into these simple units for the body to use them. And so these are going to be found in green vegetables, in beans like these chickpeas, whole grains like these oats, or tubers like the sweet potato and the half-eaten sweet potato I have sitting next to my backpack over there. Don't worry about it. All right, so we have our complex and our simple. But if we zoom in to complex carbohydrates, it actually ends up getting a lot more complicated. But one subcategory of complex carbohydrates that I want to focus on is fiber. And so fiber is really unique because it's a type of complex carbohydrate that has all these bonds between these different sugar rings, but fiber is special because it sometimes has linkages that actually are a little bit different. So I'm distinguishing the fiber-specific linkages by these orange bands here compared to the thin purple ones here. And the reason that these are so different and so important is because these are bonds that the human body can't actually break on its own. So if we start with a molecule of fiber, oversimplified here, if we are just talking about the human body and what the human body can do on its own without any help from microbes, then this fiber molecule, some of these bonds will be broken. So those are the purple ones that we saw getting cut off into these simple linkages. But these orange bonds stay because they're a little bit different. And these are special and different because only the bacteria in our guts can actually break that fiber down into the single rings that we need to use them in our body. And one of the end byproducts of this fiber metabolism that's performed by the microbes in our gut are these short-chain fatty acids. So ultimately, what's going on here is the human body by itself can't actually turn fiber into a usable short-chain fatty acid. We're entirely dependent on the microbes in our gut for this process to occur. And again, these short-chain fatty acids are so important because they end up feeding our gut cells. And it actually turns out that we can't get all the calories and nutrients out of food without our gut microbes. To illustrate this, scientists have been able to study a really, really unique and interesting system in mice. So if you have just a normal mouse, it has some gut microbes sitting in its abdomen, in its colon specifically. A normal mouse in the context of this talk is called a conventional mouse. And because I don't want to say conventional mouse for the rest of this talk, I'm just going to name her Connie. And we're going to compare this conventional mouse named Connie to what's called a germ-free mouse. And he's going to be named Jeffrey. And the reason he's called germ-free is because Jeffrey was born into a bubble and has never been exposed to microbes for his entire life. He's entirely germ-free, he's bacteria-free, he's a sterile mouse. And he has to be kept in this bubble lest he be exposed to the outside world and be colonized by microbes. And so we know that if we feed these two mice pretty much the same diet, Connie is going to have help digesting her food from the microbes in her gut, but Jeffrey is not. And as it turns out, because the gut microbiota is so important for liberating nutrients from our food, Jeffrey can actually eat more, but ultimately weighs less. Which may sound really appealing to some people, but I hope I can convince you by the end of this talk that this is not actually a favorable way to live, nor a really possible one if you want to be doing things like ever. Okay, so ultimately, you are what you eat, but really, you are what your gut microbes eat. And I just want to return to this idea that many, many things are going on inside of your body because of the activity of your gut microbes. I'll return to these two functions, the immune function and brain function, a little later in the talk. But I do want you to remember kind of the basis of why gut microbes are so important for our digestion and metabolism, and remind you that what goes on in your gut ends up affecting the rest of your body. Just a quick peek into how gut microbes can affect brain function. Just think about how hunger is really intimately coupled with your emotions and moods. Everything that goes on in your gut is going to end up affecting the rest of you. I will pause here very briefly for questions on the first part of my talk. Yes?
How does Jeffrey get any food?
How does Jeffrey get any food? So actually, companies will make mouse chow, and they will actually send it through this really ridiculously hot oven called an autoclave to completely sterilize it. They'll ship it in a sterile container, and you put that into a bubble, you sterilize that bubble, and then you open that bubble into Jeffrey's bubble, and then you only open the package once the package is inside Jeffrey's bubble. Scientists work very hard to make sure that no microbe ever comes into contact with these bugs. Any other questions? Yes?
I heard recently that it was the soluble fiber specifically that the microbes were looking for and not the insoluble. Is that, am I jumping the gun, or can you talk a little more about that?
Yeah, that's a great question. So the question is about whether it's soluble fiber or insoluble fiber that's actually important for feeding the gut microbiota. And the short answer is it's both, but it's a little more complicated than that. So there are two types of fiber, soluble fiber and insoluble fiber. As you might be able to guess, what differentiates them is whether or not they're soluble in water. But soluble fiber is going to be pretty much all fermentable. And by fermentable, I mean they can be turned into short-chain fatty acids. The whole process of turning fiber into short-chain fatty acids is generally termed fermentation. But there is some insoluble fiber that can also undergo fermentation. But it's not a catch-all in that category. The main difference between soluble fiber and insoluble fiber in terms of the effect it has on our body, in case you're curious. So the soluble fiber is going to kind of go through the ringer in terms of the gut microbiota, and that really helps soften stool and make it easier to pass stool. The insoluble fiber is actually going to bulk up our feces and give it more mass and kind of structure. And so we need both to have normal bowel movements. And one negative thing about fiber supplements is they don't often do a good job of getting the ratios of those right. But both are found in very nice ratios in the whole foods in which fiber is normally present, so fruits, vegetables, whole grains. Any other questions before I move on? Okay. So let's talk about how we actually acquire these super important gut microbes in the first place. So when we are growing inside of our mothers, it's generally believed that the womb, the inside of the uterus, is actually a sterile place. So that's the actual inside of our body. We are no longer functioning in the hole of the donut. We're in like the cakey, soft interior, and there are no microbes at this point. But when we're born, that is our first exposure to the outside world, and thus our first exposure to microbes. And how does this actually happen? What is our first big encounter with microbes? Well, for those of you who have gone through childbirth, what I'm about to tell you is maybe not a surprising thing. I have not been through it myself, but reading about this made me feel differently about my own body. So during vaginal birth, there is an entire human passing through your pelvic area, and a lot of the barriers that normally separate one orifice from another get fairly compromised. And so when you're an infant and you're passing through the vaginal tract, you'll actually swallow a lot of the liquid that's around you, and that's going to include the liquid from your mother's vaginal tract, as well as some from the rectum, because there's often a lot of tearing between the vagina and the rectum, and yes, you are swallowing your mom's poop. But that's actually a great thing, because we actually want this to be happening. So the infant's first microbiota most resembles the mother's vaginal microbiota, but there's also that contribution from her gut microbiota, which is going to be what's passed out through the feces. Okay, so that's all well and good for babies that are born vaginally. Something that has really troubled scientists in recent years is this question. So what happens if babies are born by C-section rather than vaginally? If you're born by C-section, by definition, you're getting surgically cut out of the mother's uterus for whatever reason, and not passing through the vaginal tract. So it turns out that things shake out a little bit differently if babies are born by C-section. Babies born vaginally are inheriting mostly the mother's vaginal microbiota, but babies who are born by C-section end up inheriting a very different microbiota that actually more resembles the mother's skin. So remember that I told you that there are microbes all over the surface of our body. The biggest and most diverse population is in our colon, but if you swab your skin and let those bacteria grow up, you'll see a very different but very present population. And so this is a difference, but is that difference actually important? It turns out it probably is. And one of the main differences between these two starter microbiotas in these infants is actually a type of bacteria that is really mainly present in the mother's vagina but not on the skin, and it's called lactobacillus. And you may recognize lactobacillus from the nutritional facts of the yogurt you had this morning or whenever you last had yogurt and happened to read the container. But this is maybe not super surprising. So yogurt's very tart, it's very acidic, there's sugar in there. That's something that lactobacillus really thrives on. And accordingly, not to get too graphic, but the inside of the vagina more or less molecularly resembles yogurt. It's also kind of low in pH, kind of acidic. Does not look the same, but let's stop the comparison there. Basically, lactobacillus has to be doing something really important. I'll preface this by saying that we don't know exactly what it is that lactobacillus is doing that's so important, but it does seem to be a really critical thing that the infant's first microbiota has lactobacillus in it. And how do we know that? So if we look at babies that are born by C-section and babies that are born vaginally, and we follow them for a couple years, we start to kind of track some differences between them. So we know that these babies are right off the bat pretty different. One of them is inheriting a microbiota from his or her mother's vagina, another from their mother's skin. We also see that the babies born vaginally have a more diverse initial microbiota than the babies born by C-section and getting the skin microbiota. And a few years down the road, we start to notice that the babies born by C-section have much higher rates of obesity and asthma. And it's really, really hard to look in detail and say for sure this is due to the absence of lactobacillus or something like that, but these associations have repeated over and over, and it's something that's drawing a lot of concern from scientists. So it does seem that the early microbiota has a really big impact even later in life. And it's not just mode of delivery that can have an effect on the early microbiota. Another that's drawn a lot of attention is early feeding in infants. So a lot of infants will be breastfed and be exposed to a certain set of microbes that way. And the really important microbes in this case are actually coming in breast milk. So breast milk is actually full of microbes. And so is the skin surrounding the mother's nipple. So contact with both the breast milk and the mother's breast is exposing the infant to a very specific population of microbes. On the other hand, if infants are fed with formula, they're not getting the same exposure to microbes, and they'll of course still get colonized, they're still out in the world, but it's going to be a very different set of bacteria that these infants are getting. In this case, kind of the parallel with the lactobacillus that we're seeing that was so important in the vaginal microbiota, the bacteria that seems to be super important in the case of breastfeeding is a type of bacteria called bifidobacterium. And we actually do know a lot more about why bifidobacterium is so important in breast milk. And we know that it's because bifidobacterium is responsible for the production of a ton of short-chain fatty acids. I told you those would come back. And so this is so important for the infant because we know that the infant is not only developing all their other organ systems, but they have to develop a fully functioning immune system and a fully functioning digestive tract. And remember that those short-chain fatty acids are super important for feeding our gut cells and making sure our immune cells are functioning well all over our body. But the infants that are being fed with formula aren't getting the same exposure. And so change in mode of delivery and infant feeding can have huge effects on the composition of the gut microbiota. And ultimately, we don't know the exact ways in which this is working, but the presence or absence of certain types of bacteria like lactobacillus or bifidobacterium can ultimately have some pretty long-term effects on the kid's health later in life. But what's really important for me to say at this point is this is not the end of the world. There are a lot of cases in which C-sections are medically necessary. There are a lot of cases in which mothers are unable to breastfeed their children. And I don't want this talk to sound like an indictment of those women or their children. What is really good about this research is we're learning more and more about what species are important for those modes of delivery or those types of feeding. And we're trying to replicate those effects in children that are born by C-section or have to be formula fed. And so one really cool way that we're addressing the gap between babies that are born vaginally or by C-section is that it's as simple as swabbing the kid and exposing the kid to those same vaginal microbes that are so important. It's not like you have to be in the vaginal tract. All you have to do is be exposed to those vaginal microbes and to that lactobacillus. Once a baby is born by C-section, it seems incredibly effective to simply swab the inside of the mother's vagina and then just run that swab all over the baby's body. In fact, if researchers look at these babies who were born by C-section and then swabbed with their mother's vaginal microbiota, a month down the road, their microbiota look almost identical to babies born vaginally. And in the case of formula, it's as simple as adding bifidobacterium to formula. So we're kind of leapfrogging the middleman. The baby doesn't necessarily have to drink from the mother's breast to get this same effect. We can just use this as what's called a probiotic, adding beneficial bacteria to the food that we're ingesting to give the baby the same effect. The one caveat here is we don't understand the entire composition of the vaginal microbiota or the breast milk microbiota. And there could still be types of bacteria or certain molecules or nutrients that we're missing and not perfectly recapitulating, but these two medical advances have made a huge, huge difference. And while it's still too early to look at these kids 10 years down the road, some of these studies were done just last year, we're really hoping that we can address the increased prevalence in conditions like obesity and asthma in these kids. And what's also really important is this is really just a snapshot of the infant's first year or two of life. And there's no reason that a lifetime of healthy living can't restore and maintain a really healthy gut microbiota, even after these early disturbances. I'm going to pause again for questions, and after this we'll take a break. Yes?
So I feel like it's pretty trendy now to drink kombucha or kefir or any of these probiotic things, and I'm wondering if that's like actually doing anything for me.
Yeah, so what is the actual kind of possible probiotic effect of kombucha, or is it kefir? Does anybody have a consensus on this? Okay, well, the super awesome Nordic yogurt drink thing. Are there probiotic effects from drinking these things that are marketed as such? So honestly, there's a lot of hype around probiotics, from everything from yogurt to kombucha. And I think scientists generally agree, there is a lot of debate in the field, that the hype is kind of overhyped, because as you can imagine, your stomach is like full of really powerful stomach acid. A lot of the bacteria, even if they have survived the whole process of being turned into food or drink, even if they survive that, they may not survive stomach acid and make it all the way to the digestive tract. Even when they make it to the digestive tract, there are already a lot of bacteria there, and there may not be enough coming in through the yogurt to start their own population. But I will say that a lot of doctors do recommend you drink or eat probiotic things, and this can include fermented foods like kimchi or certain types of tofu, after you have something like a colonoscopy or have taken antibiotics or have in some other way cleared out your gut, because it really can't hurt to introduce beneficial microbes in that context. So I realize that was kind of a sidesteppy answer. They're generally considered to be overhyped, but they're not hurting you. Yes?
Where does the bacteria in breast milk come from? Like, is it through the diet, or how does that work?
Yeah, that's a great question. So where does the bacteria in breast milk come from? This is something that has puzzled scientists for a long time, and there's still not super firm consensus, but they believe that there are very, very small populations of bifidobacteria in the gut. So they are coming from the gut, and they're basically carried to the breast milk by immune cells, and the bacteria will kind of hitch a ride and take like a lift to the breast. Other questions? Yes?
So if, with the bifidobacteria, how does it get into the gut if, like you said, that a lot of the time in the stomach, they're like killed by a stomach acid, and there's like a whole lot of, like with breastfeeding and formula and stuff like that?
Yeah, so I think Yeah, that's a very good point. How do bacteria that we ingest even as infants make it all the way to the gut? The idea is there's always going to be some kind of what we call a bottleneck, where like you're putting in 200,000 microbes, I'm making up that number, and only like 12,000 make it to the gut. Again, totally made up number. But the idea is if you kind of flood the system with enough are gonna settle in and form a population. And if you get enough of the really important ones, like the lactobacillus and the bifidobacterium, there's gonna be a good enough environment in there that they're gonna be able to establish a population. So it's not gonna be like you receive a packaged microbiome and it is already like good to go in the right numbers in the gut. It's going to have to kind of grow on its own and flourish and be fed by the right nutrients throughout birth. And one really important thing is these infants, that's pretty much their only source of food at that point, so they're getting it like 3-4 times a day. I don't actually know how often infants breastfeed. I'm sorry. Yeah, follow-up question.
Is there fiber in breast milk that the bacteria uses to grow in the gut?
Oh, is there fiber in breast milk?
Right.
I don't think so.
So how do the bacteria in an infant grow?
Yeah, so what are the bacteria using kind of as their starter material for short chain fatty acids? So short chain fatty acid production doesn't have to occur exclusively from breaking down fiber. It can be from other types of sugars. So actually what the bifidobacterium really like in the breast milk is, I think it's called human milk oligosaccharides. Don't quote me on that, but it's something like that, something oligosaccharides, and that's their preferred food of choice. It's super concentrated in breast milk, so the breast milk is kind of packaged as like the food and the feeder, and that's actually a really good starter material for short chain fatty acids as well. Question back there.
So there's a whole food industry that sells stuff that they want us to put in our mouths, but it sounds like the stomach acid is there and is undoing that. Are we just being too squeamish, and should we all just be going right to suppositories?
How do we reframe that question? Should we just be... Okay.
Why is everyone focused on the mouth when
Yeah.
it's pretty obvious that there are all kinds of defenses on the mouth side and there are no defenses on the anus side?
Yeah, so why are we focusing on things to ingest if they have to go through the stomach acid and the whole digestive tract when we could just be doing suppositories? I think there are probably several answers to that question, several of which I'm probably not qualified to answer, but I will give it my best shot. I think one of the most important reasons is we of course want to be taking nutrients in for other reasons, and we don't fully understand how nutrients that are partially processed in the rest of our digestive tract, I don't know why I have such trouble with that word, digestive tract, are interacting with our microbes in the colon. And so maybe that food has to kind of go through this whole beautiful journey of, you know, stomach acid and all that good stuff to actually reach the microbes in a state where it's actually usable by them. Our microbes kind of like their food pre-digested.
Why aren't we
the probiotics? Oh, okay.
yogurt right in our butts?
Well, as you'll find out in a couple minutes, a lot of fecal transplants end up going in exactly that way, probably partially for that reason. For probiotics, I imagine it's going to be less marketable if you are asking people to put giant pills of stuff up their butts. It's much easier to take a pill than take an enormous suppository on a daily basis. But that's just my opinion, and I think if you want to do that startup, I will support you. Okay, any more questions before our break? Yes?
This is going back a little bit earlier.
Yeah.
So with germ-free mice, they tend to be skinnier, but then, so why do infants if they have a messed up gut microbiome, why do they tend to be more obese?
Yeah, that's a great question. So if we know that germ-free mice don't have a gut microbiota and they tend to be thinner because of it, why is it that babies who are maybe born by C-section or are formula fed tend to exhibit obesity? That's a really great question, but I think the one really important difference here is that it's not like the infants that are born or fed through these alternative methods lack a gut microbiota. They have one, it just looks very, very different. And it may even be that they have the same number of microbes in their gut, but they're lacking a very specific population of lactobacillus or bifidobacterium, and that the place of those kinds of microbes are being taken up by something else that is really, really efficient at like just extracting a ton of calories from the food. And that's, you know, just one idea. It could be a number of factors. Another thing that I don't have time to go into in this talk is that a lot of those conditions, including obesity and asthma, actually seem to have an autoimmune component where the immune system doesn't really understand that our bodies are not something that we are meant to attack. And so that's especially true of allergies and asthma, you know, an inappropriate reaction, basically. And it seems that our gut microbes, when in the right composition, are really important for telling the immune system to calm down when it's supposed to. But I'm happy to talk to you more about that during the break if you want. All right, so let's talk about fecal transplants. This is maybe my favorite part of the talk, but mostly because I get to make the most disgusting jokes. All right, so all I want to remind you of as we start back up again is that the gut microbiota has a huge impact on health, whether that's controlling our digestion, making sure our immune system is functioning properly, or contributing to our brain health. It's doing a ton of different things. In fact, it does so many things in the human body that scientists have started to consider it basically as an essential organ on par with your liver or your heart or lungs or kidneys. And what happens if one of these organs can't function? We can actually replace it now with some pretty incredible technology. But a fecal transplant is not going to be the same as any other organ transplant. So what does it actually involve? You might be picturing a poop smoothie. And I'm going to tell you that it's not a poop smoothie. Kind of. So I'm going to give you kind of a basic recipe for a fecal transplant, but my huge disclaimer for you now is please do not do this at home. I am not telling you to do this at home. I'm going to say that multiple times during this lecture. I am not advising you to harvest your own feces at home. I am no way qualified to tell you to do that, nor will I be collecting your feces for a poop transplant. All right. So, I'm going to start off. First ingredient in our recipe is just a cup of feces, plain old run-of-the-mill feces, but I'm putting an asterisk here because we don't actually just want any old run-of-the-mill feces. We want feces that's been screened, so we're not just grabbing poop off the sidewalk or out of the last toilet bowl that hasn't been flushed in your vicinity. We want to make sure that this poop is healthy because ideally you're performing a fecal transplant to enhance your own health or enhance someone else's health. We want to make sure we're actually using something good. Just like an organ has to go through rigorous screening before it's transplanted, so does feces. And actually, the ideal feces is actually going to be from a similar source as to any other organ transplant, someone who looks as much like you as possible. And that doesn't just mean like, oh, we both have beards, we're good. I'm talking about genetics, because so many things go into how the gut microbiota forms. It's really, really critical that we make it as similar to your starting healthy microbiota or something equivalent to what that theoretically might be as possible. And so ideally this is someone who shares some DNA with you and maybe even lives in your same house so that you've been exposed to the same microbes on a day-to-day basis. So we have our screened feces. We're going to add an emulsifier, and that can really just be water or milk. Going to blend it up. And then we're going to grab even just a coffee filter, which is actually what they use in a lot of labs, and just filter out and discard the solids. And by solids, I'm talking about the stuff that you typically associate with the site of poop, all that bulky stuff, that insoluble fiber, and all the rest of the food material that you didn't end up absorbing into your body. We don't actually need that because that's a lot of plant material, a lot of food material. What we want is what comes out the other end of that filter, the bacteria that were in that poop. And then we transplant it. And as I mentioned before, this can actually go in through either end. The most common way to do this is through a suppository or reverse enema, because as the man in the orange jacket back here said, that actually is the most efficient way to get it into the location of choice, which is the colon. It's right before the rectum. Why not just go in through the back door? Alternatively, you can actually use a nasal tube. You can package it into a pill and swallow it. But again, that might have other consequences because it's going to have to pass through your entire digestive system first. And so usually the preferred method of choice is through the anus. Okay, and now this sounds like maybe a pretty intense idea. It's really only in the last 50 years or so that this has kind of made an appearance in modern medicine, but fecal transplants have actually been around for a lot longer than you might think. It turns out that people have been doing this for a really long time. In the 4th century in China, you can find writings of something called golden syrup or yellow soup, and this was used as a cure-all for gastrointestinal disease. And just to make this abundantly clear to you, it was basically just poop slurred into warm water and people would drink it straight. You can understand why they used a euphemism to name it. And as recently as World War II, German soldiers were actually ingesting camel feces to treat dysentery. Okay, so these things did happen. I am not advising these as methods for modern fecal transplants, and there are many reasons why we have abandoned these techniques. What is really interesting though is they must have worked, otherwise they wouldn't have been written down and recorded in history. They were actually having a measurable effect. The big difference is they were basically taking in straight feces rather than filtering out all the mainly unsavory stuff that we are trying to get rid of today. All right, so accelerating back into modern times, why did fecal transplants become such a big deal in the past half century or so? And it turns out that fecal transplants have been such a big deal because of the condition I kind of teased for you at the beginning of the lecture. And I'm going to finally reveal what that condition was. So our villain for this portion of the talk is a bacterium called Clostridium difficile. And I'm going to call it C. diff for the rest of the talk, just for simplicity's sake. And this is a pathogenic type of bacteria that is ingested through the fecal-oral route. So if you have contaminated food or water, there's another way to get this that I'll get to in a second. But basically, this bacteria ends up in your colon in the large intestine where your gut microbiota is normally living. And if it has the opportunity to take over, it will. And what happens at that point is some pretty terrible diarrhea and inflammation. It can actually cause a condition called toxic megacolon that is lethal in a lot of cases. It's a really, really serious condition. And a lot of the ways that people end up with Clostridium difficile is from antibiotic misuse. So actually a very common phenomenon. Doctors actually estimate that 50% of cases in which people are using antibiotics, they're using them improperly. And there are about 500,000 cases of C. diff a year. Okay, so if we are talking about C. diff and its role as the villain in our story, let's talk about how we actually acquire C. diff. If it's happening at such high rates in the United States alone, it must be coming from somewhere. And it turns out there are kind of two paths to C. diff. The first is it can already be living inside of you at a very, very, very low percentage. There might be just a few of them in there compared to the hundreds of trillions of other good bacteria that are in your gut that are kind of keeping its levels low enough that you're not exhibiting symptoms. At this point, you're what's called an asymptomatic carrier because you're asymptomatically carrying the C. diff. And what I find really fascinating about this is about 2 to 5% of the population of the entire world is carrying C. diff in their colons, but they're not exhibiting symptoms. So this is not necessarily something that can happen to anyone, but it's interesting that there are a lot of microbiota out there that we know are kind of inherently resilient against C. diff. They have it in their system, but it's not actually affecting them in a bad way. And so how do these people who have this low level of C. diff in their intestine actually progress to full-on disease? Well, I kind of already hinted at this before, but the most common way is if they take antibiotics. They either take too much, too little, on the wrong schedule, just any kind of improper use of antibiotics. And because antibiotics are what we use to treat bacterial infections, they're going to wipe out huge populations of bacteria. And unfortunately, antibiotics can't distinguish between the good bacteria we harbor in our guts and pathogens like C. diff. And so they can actually wipe out the good members of our gut microbiota and leave us with a lot of space for C. diff to take over. And this may seem a little counterintuitive at first. If antibiotics are working against bacteria, why isn't it killing the C. diff? It turns out that C. diff is really, really hardy. It's got a lot of basically bacterial armor, and it's resistant to a lot of antibiotics. And I'll get into this a little bit more. But what I want you to know here is that antibiotics can often wipe out the good members of our gut microbiota and leave a lot of room for C. diff to overpopulate. And then at this point, this person is going to have C. diff disease. So that's kind of route number one. The second way to get C. diff is maybe you're part of that 95 to 98% of the population that isn't starting off with C. diff in your intestines. How are you actually going to acquire that C. diff in the first place? One of the most popular places for C. diff to hang out is, ironically, the hospital. And this is actually due in part to the fact that C. diff is so hardy. C. diff can actually form what are called spores, and that's a term we normally associate with plants, but it turns out that bacteria can enter this dormant state when they realize they're not in their ideal environment. So in this case for C. diff, that's anywhere outside the human body. They think, it's dry, there isn't a lot of food around, I'm kind of gonna hibernate for a while, put up a lot of armor, and wait until things get good again. The thing is, these spores are incredibly difficult to kill, including with modern cleaning technology, with antibiotics, and so they end up all over hospitals because if you have C. diff, you're probably going to go to the hospital, and if you have diarrhea in the hospital, you are shedding C. diff everywhere. And so everywhere from hospital beds to the hands of healthcare workers can be contaminated with C. diff. And if someone else comes to the hospital because they fractured their ankle or for whatever other reason are in the hospital and end up taking antibiotics while they're there, they can actually get C. diff in their system. And once again, we kind of return to this base formula where the C. diff is free to take over an antibiotic-cleared environment and the disease takes over. And so here I'll remind you that once you have C. diff, it can be incredibly difficult to treat. The statistic I quoted to you at the beginning of the lecture is that 20 to 35% of C. diff cases are recurrent and unresponsive to drugs. In some cases, you can treat them with other kinds of very powerful antibiotics that actually will affect the C. diff despite it being very hardy against other drugs. But a lot of times, the C. diff will actually come back, and once it comes back for a second time, it's more likely to come back for a third, a fourth, a fifth, a sixth time. And then what you're left with is really severe symptoms, including diarrhea, inflammation, and possibly death. This sounds like a pretty dire situation, and it really is for almost 500,000 people across the country every year. But here's where fecal transplants come in, because we know that if an important organ can't function, it may need replacing. And I do want to preface this by saying that someday in the future, it may be as easy as zeroing in on one nutrient or one molecule or even one kind of bacteria that is really good at stamping C. diff out in the intestine. But right now, we don't yet know why some gut microbiota are resilient against C. diff and others aren't. So remember that 2 to 5% of the population that has C. diff in their intestines, but they're not exhibiting symptoms. They could go their entire lives without having a flare-up, even if they take antibiotics. And we don't know that for sure, but some of these people are living out there and they're perfectly healthy. All we know is that they have a microbiota that is resilient against C. diff, and we can't really zoom in much further than that. So maybe the best solution is just to transfer the whole thing that we know is healthy rather than taking a gamble with the individual pieces. And so what happens from this point on is we really want to get a healthy microbiota into the person with C. diff to restore their normal healthy system and hopefully restore a resilient gut microbiota that can make sure that the C. diff is unable to take hold in this person's colon. And so what's going to happen is we're going to find a friend, screen that person, make sure their feces are healthy and they're not carrying something else weird or unexpected. And then we are going to transplant it, and I won't go into a ton of detail about what happens in between there, but the idea is that we're restoring a healthy gut microbiota that will now keep that C. diff in check. Is there a question back there?
Do we want to find a friend who is a symptom-free carrier of C. diff, or one who is clean of C. diff?
Yeah, good question. So do we want to make sure it's a person who's asymptomatically carrying C. diff, or does it not really matter? It doesn't really matter, because so that 95 to 98% of the population that doesn't have C. diff in their system, it's not like we have a guarantee that they're going to be susceptible once we introduce it into their system. There's a good chance that they aren't. And because the screening process is so rigorous, we just want to find someone who's healthy and we can restore that gut microbiota, and ideally we're just competing out the C. diff by putting in a lot of bacteria that are going to take up the nutrients and the space that the C. diff would otherwise be trying to occupy. Because remember that the C. diff wasn't able to take over in the first place unless all that space and food was kind of cleared out. Okay, so, and that, I think the beautiful thing about this is, even though we know that maybe only 60% of C. diff cases that are treated with traditional drugs can actually be cured, 90% of C. diff motivated fecal transplants end in complete remission. And that's with just one dose. One reverse enema, one suppository, it's unpleasant for a little bit, and then it's gone. No more diarrhea, no more inflammation. And even though C. diff is the only FDA approved condition that we are currently using fecal transplants to treat, there are other conditions that are in clinical trials right now that are also showing incredibly promising results. So 90% of C. diff cases are treated, 60% of ulcerative colitis is treated, and 70% of irritable bowel syndrome. And I realize that the 60 and 70 kind of pale in comparison to the 90, but I think this is especially striking given that these two bottom conditions don't actually have a real cure right now. We have drugs that we can use to treat the symptoms of these diseases, but no real cure. And if this ends up having as high a success rate in future trials, that's an enormous difference for thousands of people across the country. And so I want to return to this slide where I kind of gave you an abbreviated and non-comprehensive list of many of the conditions in which we know the gut microbiota is altered in some way. And while a lot of these are still in preliminary trials, or we haven't started doing trials with fecal transplants yet, the fact that we know that the gut microbiota changes to something that's potentially unhealthy in some of these syndromes or conditions means that these are all potential targets for fecal transplants in the future. And we could be making an enormous difference in everything from mental health to disorders of metabolism to things like allergies. So really, the sky's the limit when it comes to fecal transplants. And ultimately, one of the main thoughts I want to leave you with fecal transplants is one man's trash can really be another's treasure. The beautiful thing about fecal transplants is we're using material that would otherwise be flushed down the toilet in most cases. I'm not here to judge what you do with your feces. But of course, as with any treatment, there are going to be a couple caveats that I want to bring your attention to. Those numbers I showed you from before still stand, but fecal transplants aren't perfect, and we're still doing active research to make sure we understand fully what we're trying to put into other people's bodies. There is such a thing as fecal transplant rejection, but honestly, there are very few cases in which rejection actually persists. While organ transplant rejection is a very common and dangerous thing, such doesn't seem to be the case with fecal transplants. A lot of people, as you can imagine, when they first do the reverse enema will have some abdominal symptoms, but they often clear up within 24 hours and people feel great after that. And often it just takes one dose for them to return to a completely normal life. The other caveat I want to bring up is kind of the other side of that coin, where we don't know exactly what is in the healthy microbiota from our donor that is able to kind of replace the microbiota of the recipient and restore health. So We don't know what the healthy part is, but we also are putting in basically a black box where we don't know every single component of the gut microbiota we're putting in. And there could be negative and unexpected effects. One really, really prominent example of this occurred a couple years ago. A woman actually received a fecal transplant from her overweight daughter. She was receiving the fecal transplant for her very, very severe and recurrent C. diff infection, and her daughter was completely healthy. And while the recipient's C. diff did completely clear up, within a couple months after the fecal transplant, she gained 40 pounds and still hasn't been able to lose it despite really, really intense changes in diet and exercise. It seems that she basically inherited a gut microbiota that was predisposed to obesity, and try as she might, she can't really fight the genetics of her gut microbiota. You know, this is kind of a bittersweet conclusion. Her C. diff did clear up, and now she is more or less healthy, except for the fact that she actually inherited what we now understand is an obese microbiota, and we still don't fully understand what exactly was in there that caused this rapid change.
Why wouldn't you immediately find a non-obese relative and do another one?
Well, so why wouldn't you try and do a second fecal transplant with someone who wasn't obese? That's a good question. I mean, I imagine I don't know why she didn't do that. I imagine cost was a huge factor. I imagine finding another willing donor might have been another factor. And based on the unexpected results of this fecal transplant, why take that gamble again? What if she gets C. diff, or what if she starts to develop a severe allergy to a food? You know, there could be very unintended consequences that, even if they don't manifest in the donor, in the context of her body could totally change. So it's really is Russian roulette, and maybe this is just worth it for her. But I don't know. It's a good question. Okay, but looking at this, if we kind of flip the situation on its head, there may be a question on a lot of your minds. If we know that some microbiota are predisposed to obesity, doesn't that mean that there are others that are predisposed to being very lean, and maybe we can eat whatever we want just because we have a gut microbiota that's going to keep us skinny forever? Well, that's a question that is on a lot of scientists' minds. And again, we're going to come back to the mouse model I showed you before. So we're going to consider our two mice once more. So we have Connie, who is our conventional mouse, who has the fully functioning gut microbiota, and Jeffrey, our bubble mouse, who has never been exposed to bacteria in his life. And we know that if we take Connie and transplant her microbiota into Jeffrey, he will inherit that microbiota in full. This is a really beautiful system because we're basically starting with a tabula rasa. Jeffrey is a blank slate onto which we can paint any microbiota and see what happens to Jeffrey. And so it turns out that if we start out with a donor who has a lot of extra weight, often mice and humans that are obese will have a microbiota that looks very, very different from mice and humans that are not obese. If we take this obese microbiota and put it into a lean, germ-free mouse, that mouse will actually become obese, despite eating the same amount of food. But conversely, if we start with things flipped on its head, and I know I told you before that germ-free mice tend to be a little on the smaller side, but if you eat enough, you can certainly become obese through any means. And if we now transplant the lean microbiota from the conventional mouse into the germ-free mouse, this mouse will often rapidly lose weight based on this new lean microbiota that is in the mouse. And so this is not something that we're doing in humans yet. And doctors want to approach this with a lot of caution because we do know that obesity, in some cases, not in all, unlike a lot of the other syndromes we've talked about, can be affected by things like diet and exercise. And again, that's not always true, but it is often true, and it may not be quite worth the risk yet because we, again, don't always know what we're transplanting. But this is something that people are incredibly excited about, and ultimately it may be something worth pursuing in the future. But again, we don't know yet why some gut microbiota are resilient against C. diff and others aren't. Similarly, we don't know the same thing about why some are predisposed to obesity and why some are not. We just don't know all of what we're transplanting. That being said, I realize that is a caveat, that's kind of a double-edged sword here, but these numbers from before still hold incredibly true, and ultimately fecal transplants are an extremely promising strategy to treat a lot of diseases that currently have no cure. So I want to finish up my talk by giving a couple really quick examples about some of the other ways that the gut microbiota can affect health and some of the potential future applications of fecal transplants. And now, none of these are have really left the lab yet, and so I can't provide you with a lot of human-centric data, but there are some really exciting findings going on in this field, and I hope I can give you a little taste of that. So kind of returning to this slide from before, this is my big overview slide of all the different ways, and this is not comprehensive, the different ways the gut microbiota can affect our health in these broad overarching categories. I want to give you an example of how the gut microbiota can affect immune function, and then I'm going to give you an example of how the gut microbiota can affect brain function and behavior. So starting off with immune function, the example we're going to use today is actually cancer. So kind of taking a step back, one thing that may be a little surprising is that our bodies are actually not too shabby at fighting off cancer on their own. Cancer often is able to take over our bodies and run amok, as many of us know, but our immune cells, along with recognizing foreign things that shouldn't be in our body, can actually tell when our cells are growing out of control and basically behaving like abnormal cells. The immune system is all about normalcy, and that can manifest in both strangers and erratic behavior in familiar people. So we know that immune cells help fight off cancer. And one recent type of treatment that has taken advantage of this fact is called immunotherapy. And so there's a certain class of cancer drugs called immunotherapy drugs that actually kick the immune system into high gear. They can help the immune system along and make sure that the immune system is powerful and functioning enough to drive off cancer cells in some cases. And there are actually some really good lectures and articles on our website, sitinboston.com, if you're curious about this topic and want to learn more. I am not a cancer person, but this stuff is really amazing. And so we know that the immune system affects cancer, but the other link that we have to draw here is we know that the immune system is basically trained by the gut microbiota. I won't go into a ton of detail here, but immune systems can't function properly without a properly functioning gut microbiota. There are a lot of immune cells in the gut, and like I mentioned before, the short-chain fatty acids that come out of fiber actually help bolster immune cell activity, and that's one way in which the gut microbiota can affect immunity. And so accordingly, if we know that there's kind of this link between the gut microbiota and the effects of immunotherapy drugs, it may not be surprising that the composition of your gut microbiota can actually dictate how you respond to these types of drugs in a clinical setting. And they've actually done studies showing that if you have a population of patients that is responding really well to immunotherapy and a population of patients that is responding very poorly to immunotherapy and is thus resistant to the immunotherapy, they can take the gut microbiota of those two populations of patients, put them into germ-free mice, and give those mice tumors, and show that the mice that receive the gut microbiota from the people who are responsive to drugs will also be responsive to drugs, and the mice receiving the resistant microbiota will not respond to the cancer drugs and will ultimately die from the cancer. So this isn't something that we're able to pursue in the clinic quite yet. The results are still very preliminary, but it's looking incredibly promising. The second example I want to give you is about brain function and behavior. And I'm going to return very briefly to the slide I showed you before, showing you that one of the byproducts of fiber metabolism by bacteria in your gut is the production of the short-chain fatty acids that have come up again and again in my talk. And one really important thing that short-chain fatty acids do that I didn't mention before is that they can actually drive the production of a molecule called serotonin. And I'm showing you a dashed line here because I don't want to give you the impression that short-chain fatty acids ever turn into serotonin. That's not the case. Rather, short-chain fatty acids feed cells that are able to make serotonin from other molecules. But ultimately, because there is this connection between short-chain fatty acids and serotonin, that actually has huge implications for our brain. And the reason for that is serotonin may sound familiar to you because It's a molecule that actually signals in the brain. It's often called the happy hormone. It affects mood, appetite, and sleep, among many other things. But what a lot of people don't know is that even though serotonin's best characterized role is in the brain, about 90% of serotonin is actually manufactured in the gut. And that serotonin can actually travel up through the brain through various ways. And our brain does produce that last 10% of serotonin, but it shouldn't surprise you to learn that that 90% of serotonin, even though it's having far-reaching effects all across the body, can have an effect on the brain. And so this is really, really interesting to scientists because serotonin is actually a target of a lot of antidepressant drugs that work to increase the amount of serotonin in the body. And scientists have actually shown that if you take the gut microbiota from someone who suffers from major depression and you put that into Jeffrey, our germ-free mouse, these mice will actually start to exhibit depressive behaviors. They'll get anxious, they'll start pulling out their fur, they'll stop eating, they'll stop running on their wheels. And I mean, this is honestly kind of a sad study to conclude on, but if you again think about this study in reverse, this is the idea that our gut microbiota could be helping us produce serotonin for people who can't naturally produce it on their own due to some chemical imbalance or whatever it is. The gut microbiota could ultimately be affecting our mood. And I also want to draw attention to the fact that I really hope that this is something that can kind of upend a lot of the stigma about depression. It's not a choice to be depressed. It can actually have really, really close tie-ins to what's going on the inside of our body and be something that's entirely out of our control. But this is a potential new treatment that could really make a huge difference for a lot of people. That's really the last part of my talk that I have to show you, but I want to end this by kind of recapping a couple things. The gut microbiota plays an essential role in our health and is thus now considered kind of one of the vital organs that's essential inside of our bodies. The early disturbances in the gut microbiota that can be affected by antibiotics, type of feeding, and mode of delivery can have really lasting impacts on our health. But at the same time, we know that even if we do undergo these disturbances either early or later in life, it is possible to ultimately correct these imbalances through treatments like fecal transplants and making sure our gut microbiota is well fed and well taken care of. And so the last thing I want to leave you with is my super corny statement. I hope I've convinced you that all this hype about the gut microbiota is flush with success and not just full of crap. And I'll break for a last round of questions. Yes?
Do you have any thoughts on how fasting interplays with gut microbiota?
Yeah, so how does fasting interact with the gut microbiota? That's a great question, and that's something that is being actively studied right now. I'll admit that that's not something I personally know a ton about, but there has been a lot of research on how fasting can affect longevity and avoiding like big spikes in blood sugar. So one reason that scientists aren't super excited about eating a diet that is mainly rich in simple carbohydrates, so those are like the added sugars and high fructose corn syrup, all that stuff, is partially because that can overfeed certain populations of gut microbes that can ultimately have negative effects on the immune system and even mood and even the sleep-wake cycle. But the idea is that fasting is one of the other ends of the extremes on that scale, and there's not a lot of research on how much better that is than just like eating moderately and healthfully, but that is something that people are looking into. And I realize I didn't completely answer your question, but it's a field of active research. Yeah. Yes?
So, like, how does the government regulate fecal transplants, and like, does it have to be approved for different diseases? Or?
Yeah, that's a great question. So how does the government regulate fecal transplants? So this is all under the purview of the FDA, and I don't know the actual regulation literature as well as I should, but what I understand is that the FDA only, like in the past 10-ish years, approved it for C. diff. That's the only thing it's approved for, and they actually backed up on the allowances in the past couple of years and increased the stringency of the screening. That being said, there are a lot of doctors out there fighting for this to be an FDA-approved treatment for especially ulcerative colitis, other inflammatory bowel diseases, and irritable bowel syndrome, because those are the things that have the most studies behind them. Also, there are a lot of places there are basically stool banks that are opening all across the country that are collecting healthy screened stool samples in anticipation of more people needing fecal transplants for C. diff and beyond. There's even one started by a couple grad students out of MIT called Open Biome, if any of you are looking to make a charitable donation.
Is there a deduction for that?
I don't actually know. I think they do pay people. Yeah, I think they do pay people. So, but it's very hard to get in. The acceptance rate is very low, as you might imagine. They want to make sure everything they're getting is very, very healthy. Yes?
So you mentioned the coffee filter thing for the fecal transplant. There must be human cells from the donor that are in the original sample.
Yes.
Some of them probably make it through a coffee filter. So are most of these transplants some of the human cells from the donor into the gut of the recipient? So
are human cells from the donor ending up in the recipient because they end up passing through that coffee filter apparatus? I imagine the answer must be yes.
Are we worried about that? Should we care?
Yeah, that's a good question. I'm not really sure about the potential implications there. I mean, I guess this is me kind of speaking out of my butt. And I think there are a couple things to consider. One is, if labs are being extra careful, they're probably not just using coffee filters, and there actually are what are called size exclusion filters that can actually filter out bacteria from human cells, which are about 20 times larger, and that's going to make a huge difference. But of course, some human cells are of different sizes, and I can't imagine some aren't going to slip through and contaminate the sample in some capacity. But that being said, they're going to be, one, present in a very, very low proportion, and two, the ways that they're being put inside of a person, they're being put in environments that are never meant to be sterile. Remember, we're staying on the outside of our body, and the outsides of our bodies come into contact with other people's cells all the time. Every time we brush up against someone, every time we share a toilet seat with someone, every time we share a bath sponge. And so I imagine that the risk for that is going to be much lower than, for instance, you may be likening this to a transplant rejection of someone's liver or something like that. But I mean, I think it's a really interesting question. I don't know if there are other potential consequences there. Yes?
Yeah, just along with my first question, a lot of the time getting FDA approval and going through clinical trials is really, really expensive, and here people aren't going to be making money, right? Because it's like poop, there's no one making a drug and selling it. So do you know how that gets funded, or who pays for that?
Ooh, how is fecal transplant research getting funded? From my understanding,
the approval process as well.
Oh, the approval process. That is something I know very little about, but I mean, I do know, at least on the research end of things, this people can't get enough of the poop. There are gut microbiota labs all across the country, and it's one of the hottest research fields. So I feel like that at least is garnering attention from potential funders and venture capitalists and whomever else maybe. Cool. Yeah. All right, well, if there are no further questions, thank you so much for coming, and please fill out a survey. Thank you.